Yes, I will be talking about something that is quite new to me because I, as the introduction said, I was doing slightly different things in the past. I started as an astronomer. I was doing quite a lot of nuclear physics and general relativity solutions of compact objects. Then I switched fields to gravitational wave detection, and now kind of try to combine that since it actually started to work. We have some detections with some new data analysis methods. So that's the topic of today. So I will basically present you today's presentation. This is kind of a very rudimentary plan. I want to first start with the introduction to what actually these detectors are doing, what they can do, and what they maybe cannot do. We'll talk somehow about traditional data analysis techniques, mostly matched filtering, and then new approaches, maybe machine learning neural networks, and then some results that we got just recently, and some papers are not even published, but so we have this very beautiful triangles that are a few kilometers length. They are full of vacuum, and basically they are designed to measure space-time distances. So this is, if you imagine that you have three falling bodies, like those apples, two apples are falling here, you can measure the distance between them using time of flight of photons, basically measure space-time distance, and then discover that the space-time is actually shrinking or expanding, so the gravitational wave is coming through the system. So now we have three +1 working detectors. Actually, now they are not really working because we are in the break between O4A and O4B and observational campaign, but they were observing, and I will talk about these detections in a moment. But first, I want to just compare this gravitational wave antenna with the electromagnetic antenna. So basically, here is just a simple antenna, electromagnetic one, which basically have this dipole characteristic antenna pattern. So it's sensitive into the direction that is kind of perpendicular to the antenna itself, and not very sensitive in this along this direction along this bar. And exactly the same thing is happening with the gravitational wave antenna, but it's not dipole but a quadrupole. So this is an averaged characteristic of the antenna. So one can relatively easily detect things that, signals that are coming from above or below the plane of the detector. But if they are coming like along the plane, in the plane, then the antenna is not very sensitive. So they're like sweet spots and two big sensitivity regions on the sky, if you project it on the sky, and 4 blind spots. So we either hope for seeing a signal that's coming from this direction, basically hitting the sensitivity region on the sky, or the other way around, like it was in 1708, you remember, it was detected by 2 LIGO detectors, but Virgo didn't detect the signal, but that was actually the point, because it is oriented in a relatively random way with respect to the LIGO detectors. So by non-detection of the signal, we could really very easily pinpoint it on the sky and actually see the galaxy from which the signal came. So the electromagnetic radiation was found because of the Virgo being located in this way, that it was basically in the blind spot of Virgo, because otherwise it would detect it. Okay, so this is just a kind of a little digression about the antenna itself. So yes. So now a little bit about the data. So this is a broadband spectrum detector. Basically, we detect waves that are of about 10 hertz, or let's say 20 hertz, to about a couple of thousands of hertz, which is by chance or maybe on purpose exactly like the ear can hear. So we can in fact really hear the gravitational waves in space. No one can hear your scream, but this is like a directly one can translate the gravitational waves into audio waves. So we even call it an audio bar detector because it's really like that. Of course, then this means that we detect only part of the gravitational waves that are present in the cosmos, because they have to fall into the sensitivity range of the detector. So, so this is a relatively broad range, and the signals that we are detecting either persistently here or entering the range of the detector and then basically evolving and maybe disappearing because of their physical nature. So here I basically wanted to show you that the spectrum is not very pretty when you look at it, because it contains a lot of lines and like these little spikes and things. And these are related either to, let's say, for example, electric mains in US. This is 60 hertz and harmonics, and also some calibration lines or suspension lines, because those free falling apples that I was showing you before actually are not really free falling. These are mirrors. We had last month we had this lecture by Guido about the mirrors and about measuring the impact of vacuum in the system. So they are free falling, but only in a specific direction. They can kind of move freely in the horizontal direction. So these lines are basically responsible for that. But otherwise, if the signal is strong enough, we can see it or hear it. So if we know where we are looking for in the time, in the specific time of the data, we can actually find it without any big problem, because so this is the data that is basically raw data from two LIGO detectors. And then basically if one filter out the low frequency noise, the one on this part, which is basically dominating on the side, and do a little bit of cleaning, then basically you can see the first signal. Basically, one can do it without any really complicated tools. The signal was strong enough to be that one is able to find it with some small filtering, like really very rudimentary data processing. But it's not the whole story, because the data is full of non-stationarities that we call glitches, instrumental glitches. They are not the pulsar glitches, because pulsar glitches are the changes in frequency of rotation of a radio pulsar. But these are all kinds of problematic pieces of data that are related to the detector. So there is a whole industry within the LIGO Virgo Kagra who is basically taking care of characterizing these instrumental glitches and finding the reason that they are actually appearing. Some of them are well known, and some of them are also known from where they come, because we have not only the main data channel, but we have a lot of auxiliary channels that are basically taking care of the well-being of the detector, so we can see the glitch in the auxiliary channel too, and then kind of understand whether it comes from seismic or other types of noise. So then we can either veto it or remove it or do something about it. There are glitches that we don't know from where they come. For example, the blip glitches. They happen from time to time. They look like that. It's a frequency in time kind of spectrogram. They look like that, and so they were called blip. In comparison, this is the gravitational wave signal. We call them chirps, because it's like birds are making noise. The frequency increasing signal, a chirp sound, more or less look like that in the spectrogram. So a binary system basically makes such a plot because the two bodies are orbiting each other, orbiting their center of mass faster and faster, so the frequency increases and also the amplitude increases. So this is also a chirp kind of a signal. So if we are looking for transient signals that are just appearing in the detector from time to time, we have to battle with all these other type of signals that a priori may also be astrophysical, but in fact they are not. A lot of them are not actual signals, but some sort of a transient noise. So one has to understand, or at least be able to veto them. So we are having, from astronomical point of view, a lot of interesting signals to think of. we either know the gravitational waveform of them, or we don't know the gravitational waveform, and they are either short duration or long duration. So this binary measuring spiral things are basically kind of here. These are the binaries that are radiating gravitational waves of the form that we more or less understand. Plus minus what is going on at the very merger, because, for example, for neutron stars, it depends on the equation of state, the way the very dense matter is composed, that we don't really understand, but we are hoping to see something like that in the waveform, and so and everything in between. So there are also these question marks that we are looking for, hoping for detecting an unknown waveform of unknown source, which makes it even more complicated, because we don't know what we are looking for even. But if we have many detectors, we can do the coincidence search between the detectors, and if the same signal happens in many detectors at the same time, then we can at least exclude some glitches that are happening locally because of, for example, seismic noise or something like this. So, and then, of course, there were all kinds of ways of how to find the signal. So I will talk about the matched filtering method. Assuming that we know what we are looking for, we can filter it out from the data, because we will basically effectively convolving the template with the data, and basically if they match, then we have a match basically, and we can find it even in a very noisy way. So the matched filter basically is something like that. Basically, with the data, there is a very faint signal hidden here. We have our best waveform prescription, theoretical prescription from the theory guys, and they so they give it us. They give us the template. We multiply this by the data, divide by the sensitivity, because the waveform, the detectors are sensitive in different frequencies in a different way. So we have to normalize by the sensitivity. So basically, we have to perform such an integral, which is kind of a convolution, and that's it. If there is a if there is a signal that matches the template, then we have a peak somewhere in the time domain when we are going through the time with this filter and compare it each second to find it. So this is what is being traditionally done. The only problem with that is it costs a lot of computation, because you have to do many of those matched filters to find a good match. On this slide, I wanted to just show you the other meaning of the signal to noise. It's basically rewriting this integral in such a way that basically the signal to noise is the area between this sensitivity curve and our waveform. So basically, the bigger the area, the higher the signal to noise. If at some point the signal is below the sensitivity curve, then we will not detect it, because we will not have a good enough area to claim a strong signal. Usually, we think that we say this figure of merit is signal to noise equal to 8 is the one that we can claim robustly detected and without any big problems with statistical significance. So this number 8 is a kind of a figure of merit. But of course, we have also signals that are weaker, and also those that are very much stronger, like the first one, quite strong. So so the problem with the matched filter is that to describe the waveform fully, one has to use many parameters, 15 or maybe more. So in principle, one has to go through a parameter space that is 15 dimensions, try every possible waveform to find the best one. So so the parameters are intrinsic parameters of the source are masses, spins. Black holes might have a spin, even a large one, so then it influences the waveform, because there will be some sort of a precession, coupling of spins, and other things. If there are components that allow for tidal deformability, then they may tidally deform each close enough. This is an extra term in energy emission, and the waveform them is different because they are basically emitting more energy because of loss of energy because of Taylor deformability. And also we have to go through all the inclination, orientation of the body, because gravitational wave is emitted stronger when the system is, if we are looking at the system kind of pole on, so this is the orbital angular momentum, and if it's like that, edge on in the orbit, then the signal is slightly weaker because of the first order quadruple nature of the source. So to find the best match, parameter estimate the parameters of the system, we have to basically, in principle, try all the 15 or more parameters. But at the end, we can find masses of the system, spins, and even Taylor deformabilities in higher order post-Newtonian expansions. So this is that is quite unusual in astronomy, because we measure masses very precisely, because this is the first thing that is being measured in binaries, which is not usually the case. Masses in traditional astronomy is complicated sometimes to measure. And the other thing that is different different to traditional astronomy is that the direct luminosity or loudness distance is measured because the amplitude is proportional to the amplitude, not energy. Then the amplitude, if we know what we are looking for, the template we understand, then we can basically measure the distance and infer the distance from the amplitude. So those binary systems, well described systems, are sometimes called standard sirens, similarly to standard candles in electromagnetic astronomy. So this makes this tool, the gravitational waves, kind of interesting because of slightly different things that may be compared with the traditional astronomy. Okay, so this is a little bit of an introduction, and so this is some kind of a summary of what was done so far. 3 observing runs since 2015, and so this plot basically summarizes masses of objects that were detected. There are a few, so these orange ones are neutron stars because they fall into a range of neutron star masses. Some of them are, we don't know what, because they are between 2 and 5 in the so-called lower mass gap between neutron stars and black holes. So they may be probably black holes that were created in a mysterious way, or are maybe an origin of previous mergers of neutron stars. So this is a very interesting region. And then there are, let's say, normal black holes that everybody are already used to, and there are also very heavy black holes, heavy in the sense of intermediate mass black holes, higher than 100 something solar masses, that again may be created in hierarchical mergers of many black holes. So this is some kind of more or less about 100 measurements or 100 events recorded so far in these 3 runs, and now we are in the next run, which is more sensitive. So the detectors are reaching farther in distance, so they are basically encompassing a larger volume. So this is a predicted increase of sensitivity. So we can measure the same amplitude but at a larger distance. So basically it scales as a cube because of volume. So we predict that in 04 we'll have like 300 new events in 1 year, comparable to, let's say, 3. So far it's kind of going okay because we already have 100, so it's more or less on track. And then of course.
What are the green points that I can see?
So they probably, yeah. So the green ones are electromagnetic neutron stars. So masses measured in electromagnetic domain of neutron stars.
Oh.
So sorry, I didn't explain that well. So this is a comparison of electromagnetic masses, and also black holes are here. The red ones are black holes measured in the electromagnetic observations, for example, in accretion disk and all kinds of other things.
These are binaries, neutron star
Yes,
binaries.
yes. So radio pulsars, double pulsar, these heavy ones, measured with the Shapiro delay and all kinds of other things. So basically, this is to I think the author of this plot had to kind of plot it somehow. So I mean, this axis. So this axis doesn't really matter. This is just to spread them to see how many of them are. What matters is this kind of like the histogram of this. What is interesting to me is that we are basically reaching into this region that is not well probed in electromagnetic, and also until some time there was this claim that there is a mass gap. There is a gap between lowest black hole masses and the highest neutron star masses, because a neutron star cannot have any mass. It will be at some point. It will the matter will make we cannot sustain the gravity for a specific critical mass. It will collapse to a black hole. So there is surely some sort of a maximum mass for neutron stars, but maybe also a minimum mass for black holes, because black holes are also somehow created, maybe in supernova, maybe in a different way. So, well, but maybe not. So that's the big question mark here. So yes. So this is the story of the so-called second generation detectors, LIGO, Virgo, Kagrad, ground-based detectors of, let's say, a few kilometers length. The length is important because we are measuring the amplitude that we are measuring is the difference in length of arms divided by the length. So the bigger the detector, the more sensitive the detector, more or less, in first order. So the plan is to build a bigger detector, and the bigger detector will be, for example, Einstein telescope. So this plot is also not yes. So this basically is to show that Einstein telescope will basically, so the green is Einstein telescope, will reach and be able to be sensitive to basically the whole population of binaries in the universe, or the majority of it. For example, black hole binaries will all be inside the horizon of the Einstein telescope, because it will be so sensitive that it will be reaching to the redshift factors of few 10 or even more. So as you can see here, and so we will be able to probe the neutron star binaries, which will be created during the cosmic time from early universe until now, all the black holes and so on and so on. So this will mean that we will not have 100 detections per year, but 1 million detections per year. And then this is a problem that you cannot solve with another student, because it's just too many detections to analyze. There is not enough computing power to use much filter out all the signals which will be coming at the same time, basically every detection, one detection per minute or something like that, and they would be long, because the Einstein telescope will have a lower frequency in the sensitivity. So this basically is a slide to say that this new incoming problem demands new solutions. And so the new solutions is maybe try to automatize things. So basically it's about taking the data, calibrated data, and running it through a faster algorithm, better suited to many detections at the same time, and to be able to claim that there is something in the data. So I will today talk about signal detection and classification, parameter estimation, and the noise, which is basically this artificial intelligence part. So, and I will start with something that is called a convolutional neural network. Convolution is this thing that we already saw before. So this is like a piece of template that we are sliding through the data and convolve with it to find if there is something that is kind of correlating with it. So this CNNs, convolutional neural networks, are routinely now used for classification of images, because you might have many layers of neurons, and each layer is doing kind of a scale convolution, basically first detecting some small features, then larger features, even larger, and then basically detecting the whole image, classifying the whole image, because the training of such a network would look like that we'll be inputting images of, let's say, dogs, and other images that we will say are not dogs, let's say, and either penalizing the network for correctly classifying it as a dog, or giving it some kind of a treat that it did it correctly, and in this way making it change the parameters of the neurons such that that it works. So this is basically done by having a lot of data and by force training the network to assume the weights and biases of each of the neurons that are connected with all the other neurons, so that it performs a correct classification from our point of view. So from this point of view, this neural network is a very complicated, very nonlinear function that is approximating something for us. So I'm talking about the CNS because they are relatively easy to train. The neurons are quite stupid because they have just weight and the bias, and basically they take an input, do this, and then produce an output. And then you may stack the layers on top of each other and have a large training data set and have a large network, and you have a large GPU or a CPU, and you can train to classify whatever you want at the end.
Sorry, do you have a single neural network for every kind of signal that you might have, or one for each?
So one for the type, let's say. Yes, and I will talk about that. So I for example, will show you later the results for a network that is able to recognize the difference between a signal in the noise, noisy signal, very noisy, you cannot really see it by eye, let's say, versus a glitch. So it will be able to tell some sort of a probability of classification. But I know that people are just taking this kind of, this is another interesting part. You take a pre-trained network, for example, it was trained on dogs and cats. And you can then take it and retrain it slightly to be able to tell the difference between these images. Because for the network, this is, I don't know, kind of a different type of cat, and this is a different type of dog, and that's it. Basically, recognizes the colors of the pixels in different scales. So I will be talking today about not image classification, but 1D classification. So this is much closer to what the actual raw data from the detector looks like. We have a 1D time series. This is the only good thing that is coming out of the detector, that the time series are sampled at the constant time, because it's an electronic signal. So basically, you have sampling, not like in astronomy that you have observation today, observation another 2 days. So you have to take that into account as well, the gaps in the data. No, here you have well sampled data, but very noisy. And it looks like that. So this is a piece of data, 1 second of the data, in which there is an event, a binary in spiral of 2 black holes of these masses, with the signal to noise, optimal signal to noise equal to 8. So this kind of a threshold value. So if it were not plotted here, you probably would not see that it's there. But so the usual thing is that you produce a lot of such examples of known waveforms and feed it to such a network that reads in the array of time, this kind of 1D time series, and either say, and this has a label. It's a signal, but without it, it would be just a noise or a glitch or something else. And then you really train it many times, and it learns the difference, because it basically recognizes some changes between the points, and is able to actually classify the piece of data a priori containing a signal as actual data containing signal. It is compatible with the match filter, the traditional one with the integral and so on. So that was done already a few years ago, and this basically kind of started. That was the first thing that people started to do. This kind of started to make this thing interesting, because you can really well find the signal in this way. And the good thing is that it is much faster than the traditional matched filter. So I now want to talk about something else, which is, you may think about it as quite naive or silly or not really useful. It's called the autoencoder. So we have the two type of, this is a neural network composed of two neural networks. This one is called encoder, and the other is called decoder. They are inside exactly like, for example, those convolutional neural networks, layers upon layers, connected with each other with the simple neurons and so on. So the only goal of autoencoder is to take the input, process it through the thing, and output something that is exactly like the input. So this is the identity function. And so basically the training goes like that, that you feed this in and you demand that the output should be as close to the input as possible. So the identity function is a trivial kind of thing, but what is interesting is that this middle part is called bottleneck or latent space. This, in principle, contains a compressed version of the input. So one can think about it as sort of a distilled, compressed information about the features of the input. So it kind of contains the parameters of the input. And then this gets interesting because you basically are feeding the images, let's say, to the encoder. There is this latent representation of the input, some sort of an array or some other data form, and then it outputs something similar to the input. The conditional part means that you can not only feed in the image, but actually the parameter that is behind the image. So this is the image of the number 3, and this is the 3 parameter, right? And then the latent space, then we can imagine it's not just a kind of a anonymous vector, but it's a distribution. We can think about it as some kind of a posterior distribution, let's say. So this, if trained correctly, it would work like that we have if we train the network, we forget about this part, completely forget. Now it's not important. And then we take points from the latent space of the trained network, and basically this part acts as a generator. It generates images that are images of number 3 that are similar, that are coming from the region of the parameter space that are related to the parameter of the number 3. So we could have here, first of all, a generator of images of the data similar to the input data, and also something that is estimating the parameters of the input with some kind of error estimate as well. So we are basically now have not only one number, but the whole surrounding, the whole distribution. We can think about confidence intervals and credible intervals and so on and so on. So this makes things very similar to the Bayesian inference. Of course, there are subtleties about it, but that's on the kind of first glance is very much like the Bayesian inference. And so this was also tried with the gravitational wave signal. So you input instead of number 3, you input the whole waveform with the parameters of the waveform, masses, spins, localization on the sky, on the angles and things like that. And then basically you can estimate how well the network is estimating the parameters of it. So it's like Bayesian Markov chain Monte Carlo going through all the parameters, but then actually you have access to this distributions very easily, and this is really much faster than the typical Markov chain Monte Carlo. They have to do a lot of tries and evaluate the match trigger many times. This is of the order of millions times faster than traditional MCMC. So this is already something practical. And also one can use the autoencoders as some sort of anomaly detectors. So if I would train the autoencoder on this typical autoencoder on, I would feed it noise all the time and demand that outside as the output, it will be noise, only similar to the input noise. Then if I would input it something which is not noise, for example, a signal, then this reaction on the output will be, oh, this is something else. I don't know it. And so this could be used as an anomaly detector. So it could be tried on signals. And so anomaly autoencoder trained on noise only detects signals as a novelty. Let's call it novelty, not anomaly, but something that it didn't see before. So this is a very crude detector done by autoencoder. Okay, so now I want to talk about how to remove this noise. So we have data that is signal hidden in the noise. So then we don't have a simple autoencoder, but the noising autoencoder. So we input. So this is our clean waveform, let's say, without noise. Then we add noise to it, corrupt it, run in the training, run through the encoder and decoder, and then we demand that on the output, it's clean again. So basically, this part performs the noising, cleaning of the time series that we have. And so then, of course, we train it, demanding a slightly different loss. So this is the penalty function. Basically, we compare the input with the output, and basically this effectively makes the network learn what is the noise and what's not noise, and what to remove and what to keep. So I will talk about a specific version of the noise answer that we worked out some time ago. So basically, it looks like that. It's time domain data. There is a signal hidden somewhere. I plotted it here to indicate that it is the green wavy thing. And this is the output by when the noise is removed. So the red waveform is the output of the denoiser. And then there is also some kind of an estimate of the error, which is called aleatoric uncertainty, which basically is how much this depends on the realization of the noise. So we tried that many times on different noises, and this orange thing is an error that comes from different, our incomplete understanding of the noise. What is important is that when you remove the denoised waveform from the original piece of data, then there's almost nothing there. So it works because it really finds the waveform. So one can think about the denoiser as a very simple, well, detector. So we tried that on many different realization of signal plus noise, and checked that that it behaves like it should. So it basically denoises properly. If there is just simple noise without any signals, then basically these pieces of data are landing for the noise SNR somewhere near zero, which means that the detector, the denoiser, is behaving properly because it produces some sort of a waveform, but the SNR of it, the SNR of the denoised waveform, in case when there is no waveform in the data, is close to zero. So we can say, like, for example, we treat everything, we set a threshold for interesting things for the denoised waveform, let's say larger than, let's say, 6 or 8. Above the noise SNR of 8, let's say, all of the denoised pieces of data actually contain a waveform. And we also tried that on the glitches. So because the idea would be to have the noises that noises the waveform, but doesn't denoise the glitches, because these are not waveforms produced by the binary systems. And again, it's a kind of a sanity check, because most of the glitches were denoised to values that are close to 0, or at least smaller than let's say 8 or something like that. So it's just a sanity check. There was one that was quite similar to the chirp, I think, so that's why it had a higher TNR. And at the end, we tried that on real detections that were not even a part of the training data set, and not even a part of the same observing graph, because we trained the noiser on data from O1, from Livingston detector, and we then tested it on data from O2, from Hanford. And you see that it kind of works. It works. Of course, it doesn't work always, because, for example, it doesn't work when the parameters of the waveforms are not compatible with the training dataset, because it doesn't know what to do with masses that are much larger or much smaller than the training dataset. But for those parameters that are within the training dataset, it kind of works. Okay, and then there is another case when the masses were much smaller and the signal was much weaker. So it also kind of tried their best. It did whatever it could. This low frequency part is not really well denoised, because we did some kind of a cut at frequencies lower than something, lower than 50 hertz. So this is kind of a poor man's way of doing detection with machine learning. I wanted to show you this because surprisingly, it kind of works on almost all the detections that we have so far. So one can do it without much filter, and that's the message. Okay, so now I will move further to recent news from the O4A. O4A ended.
I have a question. So this kind of neural networks is real time, basically?
It's very fast.
If you just send it into the machine, it tells you immediately what's coming out.
You have to, depends on what you do with the data at the beginning, but because you sometimes have to process them a little bit, like some whiten the data, but there are versions that doesn't do that. So basically, it's real time. Yeah.
But these are applied on each single.
Yes. On each. Yes. So yeah, I'm talking about. So far, this doesn't really touches the coincidence time between the detectors. What we tried is just to take data from a different detector, and so this is just a kind of a silly check whether it will work. It works because the data looks very similar for the LIGO detectors, at least. They are comparable sensitivity. They are oriented in more or less the same way, because if Livingston is like that, the Hanford is like that. So they basically are looking in the same direction. That was a choice, and not by chance, because they wanted to maximize the detection, the first detection. That was the goal, to be able to detect with both detectors in the same direction. Virgo is oriented in a random way, mostly because the farmers didn't agree on how the pipes have to go. I think that's the story. So this is the consensus between the local community. But it's good because it's it looks in a slightly different direction, so it doesn't detect when LIGO detects, which is bad, but it detects when LIGO doesn't detect. So it's okay. And I will be continuing on one detector or single detector story, because so this is a cumulative number of events in time, beginning with O1, O2, O3. Then you see the increase in sensitivity or to volume, or sensitive volume of the cosmos. And then O4A, even more sensitive detectors, and we see increase of the events. So it's almost 200 now in total. And so these are performance on duty factors for Hanford and for Livingston. Basically, they are on for, let's say, 70% of the time, and off for 30% of the time. So if you have two detector network, basically you have single detector time on, let's say 30%. In let's say 50% of the time you have two detectors working because they are on and off in random times. So and we thought when we were looking at that some time ago with collaborators, we thought like this is quite a lot of time when you have only one detector, you know? And usually this data is not really treated as like a full data. Nobody is actually taking that into account because what we want to have is this coincidence time between two or more detectors. When Virgo is in the network, then this changes. But these are data from O4A when Virgo is not observed. So you have, in principle, quite a lot of percent of time when there is only one detector working. So let's have a look at what we can do with the one detector data and well, use neural network. Because why not? Again, we took this O1 data because it's like a kind of a benchmark. And this time we have produced a few classifiers that classify three classes: noise, signal, it is a kind of a signal and faint chirp, and a big glitch, low frequency, it's big, same like it's something completely different than the chirp. So a simple three-class classifier. And for this, we have used a classical convolutional neural network, a temporal convolutional neural network, so-called TCN, that is also connecting the neurons like the CNN, but only in one direction. So it is aware of the flow of time. So it doesn't take into account information that is from the past to from the future to interfere with the past. The typical CNN basically takes whatever it has to classify, but this is a more cleverer one because it knows about the flow of time. And there is also a third version, kind of a more complicated convolutional structure with many convolutions within each other, kind of one inside each other. So and therefore it's called inception time. It's like the movie. Have one in the second structure of convolutions, and then it is able to find substructures well, it's better into kind of understanding the data than the typical CNN. So and then we run it through the data set, and we have counts when the classifier classified different classes as a signal or a noise or a glitch. So you basically, from this slide, it's basically comparison of three different outputs. When the network is classifying something with a class close to 1, so it says, yes, I'm pretty sure that this is this class, right? So we want to interpret this number as a probability that the network is outputting some sort of a probability to be classified as signal. And we have also noticed that this networks didn't really distinguish between noise and glitch, but it distinguishes the signal between these two other classes. So effectively, we have two classes only: signal versus everything else, glitch and noise. Well, we said, okay, it's good enough because we are interested in signals. And so these networks basically behave like they should, which is for the fixed false alarm rate. So we want to have false alarm rate that is comparable with the traditional searches, which is like once per day. Once per day, we are allowing it to make a mistake, to raise a false alarm. Yeah, I'm having a signal, whereas in fact it's not a signal. So it's a decent rate. We can even get lower, like 10 to the -6 would be once per month, for example, or once per week. So naturally, the stronger the signal, the better the classification efficiency. So this works as it should. And then, we have we trained that on 1 month of the LIGO O1 data, LIGO Livingston 1. But there were other 3 months in which we could use the data. So we used that for training. So we used all the data all the noise from this data in which we have injected artificially in software injected signals to test how the networks are performing, and also tested the network on the 3 detections that we had in O1. So this first one and the 2 other ones that were detected. So 150914 was detected with the probability equal to 1 because it's a very strong signal, obviously, and so on. This one that was at the beginning even not really regarded as a very strong signal, now was promoted to a real gravitational wave, 151012, was quite weak, and basically what it landed kind of with this probability, 10 to the minus, let's say, more. And then this one had masses, so it was a much longer signal with a smaller amplitude. That was not really in our training data set, so it basically was not detected as signal. We kind of said, okay, because it's not, that didn't belong to our data set, so we couldn't really demand from the network so that they make a miracle and detect it. We could probably retrain it, and then probably it would be kind of higher. Well, we didn't do. Okay, and then this pink histogram is a distribution of glitches in the same data that were classified by the community volunteer program. So basically, people looking at the data and saying that yes, this is a glitch because it looks like a glitch. It looks like this image that these images before were basically from the Gravity Spy program or Gravity Spy community volunteer initiative. So we ran this through our classifier. This is the histogram. So as we expected, most of the glitches were classified as glitches. But except one. There is this one that has this lambda equal to infinity, which means probability of being a signal equal to 1. These other cases here are our injections, so our testing sample. So we thought like, this is interesting because there is this blip that basically looks like a signal. So we looked at the glitch at this time. That was January the 4th, 2016, and it looks like that when you make a kind of a close-up. It looks like that, and this is more or less the typical blip. So we saw that doesn't really look like a blip. It looks somehow different. It looks maybe here like a blip. When you look at it closer, then kind of look kind of like more chirpy, let's say. And so and we started to look if other people actually noticed the same thing. So there was a paper before that basically analyzed the gravitational wave from binary measures in a single observatory, so in a single detector mode. And indeed, they had the same glitch. They looked at it. It was observed by only LIGO Livingstone. And so this is the original spectrogram that they have. They found the best matching waveform, subtracted it from this data. But I don't know what they actually did, but something else happened, and they basically got a very nasty residual here. So they say at the end, so they have top candidates. This is one of them. They perform some additional diagnostic to confirm that the signal morphology is consistent with the gravitational wave source, so the chirpy thing. For some cases, this diagnostic disfavors the candidates due to missing or excess power. So this is clearly a lot of excess power here, such as the case of 160104, which otherwise would have been the most significant candidate, right? So we then thought like, okay, so this is maybe something that we really have to look in more detail, and we ran this through our denoiser. The denoiser that I was showing you before. This is the red curve is the denoiser result of the piece of data, and the blue is the traditional Markov chain Monte Carlo parameter estimator called Bilby. And we, lo and behold, found something that is matching the denoising output and looks exactly like a chirp in the data. So the parameters of the sources of the system is, and also the residuals after subtracting it from the data, are quite clean. Nice. So the parameters are of the usual black hole merger. So it is consistent with black hole population observed. So I have placed here a tiny celebration because it may mean that we have actually detected a wave with this stupid robot. So yes, so this is the story so far. Quite silly, I would say, because we didn't really use much knowledge here. Basically, we have produced a lot of waveforms, put them into the data, force-fed the networks with a lot of them until they actually learn what's the difference. But what we want to do here in Ferrara with Matteo and with Francesco is to actually go one step further and implement some physics into the neural network. So I will now show a few slides that are basically a result of work of Matteo here, his master thesis and the beginning of the PhD. Something that is called physically inspired neural network. So this is a neural network that is not just a composition of stupid neurons, but it also has inbuilt some physical laws. So one can think about this as a neural network inside a differential equation. So this is not our type of equation, it's a Bejger equation, but we can think about either ordinary differential equations or some partial differential equations in which a part of it will be a neural network, and inside of this neural network, there will be those parameters that we can estimate. So we can infer directly from training such a network the parameters that are inside the differential equation. So what Matteo did in his masters, basically he took a Newtonian waveform, kind of quite simple Newtonian waveform, and trained the recurrent neural network that is type of a network that is working in time domain. Basically, it's a much more complicated neuron. It's basically a tiny Runge-Kutta integrator in each neuron that basically takes the input of the time domain and basically outputs something. And basically, time here is basically the integration integration variable. You can train it to solve this kind of evolution in frequency of such a waveform. And the loss function is the difference between the solved amplitude in time versus in frequency versus the original one. So here in the PhD time, we started to complicate that because we started to do post-Newtonian case when you have more parameters. So this df over dv starts to be more complicated, and the loss function is more complicated, but it still takes into account the physical prescription. So these are just very fresh results. When you start with a waveform that has masses of 30, so the waveform has masses of 30 and 30, and then the masses are equal. So the symmetric mass ratio is equal to 2 to this, a quarter. But if you start with a completely different sum of masses, 80, and a completely different symmetric mass ratio, the neural network is able to learn the actual evolution of the waveform and reproduce it. So this to me is very exciting. It doesn't look very exciting, but this basically looks like zero all the time because it's a difference between the real waveform and the one that is inferred. So basically, the network is performing parameter estimation from the data. This is the initial waveform, and this is the end result. Zero everywhere, which means that the difference is zero. So yes, so this is very much like it very much because this means that we will be able to really not only detect the waveform but also estimate the parameters of them using something more clever than just neural networks. It's more than just a neural network. So I will end with this slide, which is basically summary and outlook. That basically says that we have to complicate things, add noise, train it on more data, expect problems. But what I want to say is that the same techniques may be applied to all kinds of other pieces of astrophysics that has differential equations. So, and we want to try that too. So I also asked ChatGPT to write a limit